Thanks a lot, John. We'll talk about the title a bit here. Let's hear from Kajal. You already know him, so he's going to talk on the same topic a bit.
So I'm going to take a slightly different approach because I think it's lies, damn lies, and weather. None of the forecasts are working for currently. But when you take a deconstructing approach to statistics, and you have to find it out, like, where the source of it. And this is all Wikipedia. It really doesn't matter. Our knowledge is all right there, except how we apply it. So if you think through it, is that this is the person always, he started likes, damn lies, and statistics. So if you cannot do with damn lies, you can try to figure it out that how to use the statistics. And that problem persisted for a very long time. And in fact, if you think through it, that there is a episode in West Wing was exactly lies, damn lies, and statistics. And we all know, if you go and look at it, it's about the opinion poll, that people don't believe it. And we know that there are cases that, interestingly, for the last political elections, that there was a lot of confusion within our research community about producing numbers that we really don't believe, but still they come out of the numbers. So if you think through it, it's going back to a little bit of the history that where it all started. It all started the beginning of 20th century, starting with Carl Pearson, who did the correlation. Fisher started the first analysis of variance, multivariate statistics. The whole frequentist approach is based on Fisherian statistics that we all know, and then it came the holy grail of testing. And that's what the name, and another Pearson, and Egan Pearson happened to be Carl Pearson's son, built the entire testing framework that we know as of today. But that built us to the next part of it, is like how we keep building lies, damn lies, and statistics, and always miss the point that what exactly is statistics supposed to do. And then we can take data sciences and natural applications of what we do from the statistics. The final conclusion will come to the point. It's a single line, that where do we make the boundaries? So if you think through it, the challenges that we have today is basically that how we make conclusions. So what is statistically significant and therefore meaningful, acceptable, and replicable? Now, each of these things is extremely important for understanding, is that if we can't do these things in a meaningful way, it doesn't matter. Just one time I do a fancy analytics and it never works. So if you think about the criminals that goes into these spaces, and then 2 years ago, I think it started 5 years ago, but the 2 years ago, there is a huge debate into the communities about using p-values. The p-values, we all know about it, but actually there is a very, very profound lack of understanding about what p-values are. And then there is a thing called margin of error. Now, if you are all in data and research, that we know how the margin of error played a very, very significant role in making decisions. We have plus or 2 minus margin of error, and then everybody is happy because I have an overlap, and then you have a sample calibration. Sample calibration gives you a completely different ideas about the margin of error, and in the reality, it is not replicable. And this happens very much into the way that a lot of the biostatistical research about taking samples, about very, very important and profound implications into the human life, and the results are not replicable. So the challenges that comes in, and then there is confidence interval. The funny part is that all three are somewhere or other related or correlated. So I'll just want to take one example, and then I move on to the one that very, very commonly referred to in our world as a very mistaken identity about like where the lies and the damn lies comes in. So what is p-values? The p-values are not the probability of rejecting a hypothesis. It's a completely different thing. Okay? It is not itself a probability. Its significance is a convention. So we all live and breathe 5%. Every time we go and talk and understand, read, where is 5%? Where is 10%? But isn't that something very arbitrary? And if we know that what the p-values are and is, and then we can figure it out, like if you have a very, very large sample, then everything is significant. So moving on to that, you can see that there is institutions that is built onto the p-values fallacy. P-values fallacies is just nothing but using a probabilistic measurement that it says its p-value is significant. P-value itself is a probability, so being significant is a misnomer. You can't use that. So use that p-values fallacies. You use a p-hacking, which is a machine learning, try to go and find it out where the most significant p-values are. And you can always find something significant, whether it is meaningful or not. And then you move on to going into multivariate setups where you are looking at your probability and significance into a very singular context, whereas you have a multiple context. So if you wanted to compare, is that the comparisons work? And then you have a type 1 and type 2 error. These are connected, but these are like false positives and false negatives. That means is the p-value is only tells you something about type 1 error, but always ignore the type 2 error. Having said that, I wanted to pick out one example, and that's where that, that we all fall flat in terms of making the lies even better. So think about this. It's called Simpson's paradox. And Simpson's paradox is very profound in our applications. If you think through it, is that how many times? So think about a group 1, a region or any other kind of segment that we have it, and it shows you a positive trend. And then you have another group 2 that has a positive trend. But if you combine them, you have a negative trend. So the most classic examples of Simpson's paradox is actually extremely real case studies in which you have 2 procedures to do kidney stone, small kidney stone and the large kidney stones, and you have a treatment A and a treatment B. So when you apply and take the data, you find it out that for treatment A, the group 1 and group 3, they all produce the similarly better results. So whether it is a small stone or a large stone, you could always go with the treatment A. Fantastic. But if you just put this one, what happened? So we all make conclusions, we all make groups and segmentations, we do statistical analysis, we combine them, we make conclusions based on something that in our mind that thinks like it's a natural consequence, but it is not. So the lies and the damn lies and the statistics deconstructing where you can see that where the founding fathers of Fisher and Neyman and Pearson's that they came as the intent of statistics is a completely different. My time is up, but there is the line. Algorithm and statistics is not the same thing. We are moving towards a world that we're using increasingly an algorithm to do statistical analysis, but the statistical analysis is really a probabilistic understanding about your data and your sample and your behavior that projected to that, conclusions that's more meaningful and replicable. So I'll stop here.
Thanks a lot, Kajal. Lots to talk about here, so.